Well, hello everyone, and thanks for joining today's Ascendo Reliability webinar. I'm Fred Schenkelberg, and today we're going to be talking about reliability predictions. Is that look into the future, the crystal ball, or whatever method that you use, and try to nudge you a little bit towards creating useful or meaningful predictions. So that's my objective today, is to outline some of the issues and some of the benefits of doing this well, and then we'll go from there. So as we're getting started, got a little bit of housekeeping here to do, but mostly it's just to let you know that, and I'm trying to think of where my pointer is here. There it is over to the right of the title screen. There's a links information there, and there's a handful of different links in there. And I'll bring this, basically this setup again near the end of the presentation when we're talking questions and answer type stuff. But there's also the slide deck. So as many of you know, my slide decks are generally just a bunch of images and very few words, so it's usually not a standalone thing. I am recording, and there will be archives available, and you'll be able to see this afterwards if you so desire. So let me just dive right into the presentation. Good morning, Neil, and Angel, thanks for participating. I noticed you were logged in pretty early, but that's fine. And please feel free. The chat window will remain open throughout the presentation, so feel free to jump in and ask questions or comments. There's a question tab available also. You can drop stuff in there. And my intent, not always successful with this, is to make these more of a discussion. Um, we have enough people that it doesn't make sense to open up the microphones for everybody, but I probably should figure out a way to do that. Yet we've got a good crowd today, so I appreciate that. And happy Tuesday for those of you that haven't already transitioned into Wednesday. So let me find my cursor and dive in. So there's a hands up button near the top of the screen, a little person with their hand up. Use that to, have you ever been asked for or expected to provide a prediction to how long something will last before it fails, or a piece of equipment, how much useful life it has left? So just raise your hand to, how many of you have been asked to do that? Yeah, I'm seeing a handful of people so far, and hopefully the rest of you are finding that button up at the top. Uh, it's it's a it's a common task for reliability professionals or in any engineering discipline to say, well, how long will this last? And all right, so you can tap that again and put your hand down. That'll work. And yeah, I think ever since the very first engineering projects, the very first bridge, for example. So I think the first question is it strong enough? Um, and then the second is, will it last? Will it survive long enough so that 2 years from now, when I bring my ox cart across there, will it still be strong? And that's something we face all the time with all of the projects and products and systems that we're working with, is that question of, well, how long will it last? And the easiest way to do that is to um, just wait for the customers to tell you how long it lasts, but that's not always feasible. All right, forgot one other piece of housekeeping here is just recently on AscendoReliability.com, or you can find this at reliability.fm, the URL will point to a podcast network. Tim Rogers is hosting an interview program where he's interviewing quality and reliability thought leaders. Speaking of reliability, I'm in discussions with a handful of other co-hosts. Kirk, I think you're online, and Carl and Adam and Tim and I are discussing various topics in reliability engineering, and that comes out twice a week. Dare to Know is twice a month. And then you'll notice the little Accendo Reliability webinar logo at the bottom. So the archived webinars are now being streamed via podcast, and all of them are available uh, on iTunes. And Dare to Know, and speaking of reliability, is on Stitcher, and I'm not sure if Accendo is up there or not. I haven't got that confirmation yet. So another channel, another way to listen and learn, maybe good for your commute on the way in to work or as you travel, or if you're a regular podcast listener, now we've got some reliability topics for you to add to the mix. So take a listen, let me know what you think. And also, if you're, feel so inclined, please leave a rating and a review. Let us know what you think. It'd be really, really appreciated. So anyway, I almost forgot about announcing that, so I'm glad I put a slide in there. Um, So some years ago, and this is a photo I took in Italy a few years ago when I was there doing some climbing. But 25 years ago, I was asked to evaluate a heating cable that was going to go into the highway bridges in Italy. And I actually got to see some of those devices the last time I was there. I looked at the bridges, and there's a little sensor that detects temperature and moisture. So if it's cold enough and it's either snowing or raining, a heating cable network in the concrete will energize and will keep the bridge dry and keep ice from building up on the bridge. And if you live in an area that has snow and ice, you often see the sign saying the bridges are slippery or icy before the road surfaces. Well, in Italy, they reverse that. The bridges would be dry and the rest of the road would be covered in snow. But when we first got that project, I was a relatively new young engineer, and my boss, the director of engineering, walked in and said, they won't buy this unless it lasts for 20 years. Because they're not willing to um, embed it in the concrete unless it will work for 20 winter seasons. And I said, okay. Well, I'll go live in Italy for 20 years and I'll report back every year of how many of them are still working. And that was the only way I knew how to do a prediction, was go measure it. And I'd been working as a manufacturing engineer, so it was, you go do experiments and you measure yield right then and there. It was pretty quick. And he says, no, 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 you've got 6 months and you need to tell us how long this will last. And here, look for accelerated life testing. And so I was off to the library. This was pre-internet. Uh, Email was just coming available, and so I was kind of lacking a lot of resources. But I was lucky and found some good references and good papers, and some colleagues of mine at the company gave me some hints and ideas, and worked with a chemist and understood what the failure mechanism was. That our product would oxidize, basically it would break down and wouldn't be able to provide heat anymore. And so we ran a series of experiments that then, with a good model, focusing on that oxidation degradation process, uh, showed that these things would probably last 25 to 40 years, depending on the temperatures they were seeing, with a pretty good probability that they would survive, say, 30 years. So the customer was happy with that description of the possible life of the product, and our team was able to sell these into the bridges in Italy. And it only took me about 20 years before I got out there to go see them. And fortunately, the bridges were dry. When it was snowing, the bridges were clear. So I'm assuming that bridge had our product in it, but I was very happy with that. The hard part is that to know if your product, like a solar panel, is going to last for 20 years, well, it takes 20 years to find out. And a lot of us don't have that time. Uh, but we need to know this, say in 6 months. That's when this customer and our sales team were closing the deal basically to make this product for these Italians. Yet in any of our products, it's at some point, we need to make a decision. Is this going to last? Is this going to work? And that's why we do predictions. That's why we get asked to peer into the future to figure out what's going to happen. And so there's no real mystery with that. And now it comes down to, you know, can we do this? And are we good at doing this? Now, reliability predictions have been happening for years and years and years. This isn't, like I've said, it's nothing new. So let's take a quick look at, and I may have given away some of my next part of the slides here, but let's take a look at a poll. So and you can select more than one, which of these techniques do you use? There's guessing, parts count method. You could add parts count stress methodologies, doing standards-based testing. This might be a little small. Unfortunately, I'm not able to control the font size on it. Success testing or no failure testing. So you run 5 units for some period of time, and if they don't fail, they must be good. None of the above. Now, I should have added another one, is you don't do any testing, or you do something different. But yeah, I mean, we use all kinds of methods. Now, I'm surprised nobody's guessing, because that's almost always where I start, is go, well, I think it'll work. And your design engineers, when they're picking material and picking methodologies and technology, to some extent, it's based on their experience. It's a scientifically based, engineering experience based, whatever. It's a guess, right? We typically do that. But yeah, lots of parts count methods. Now, next month, I'm going to be talking about alternatives to MTBF. I should do one on alternatives to part count method, but we'll see how that goes. I'm actually pretty excited about next month's one because, as you know, I'm pretty excited. Let's see. Let me end the poll. Let me see if this will broadcast out. So, are you seeing the results? Let's see, where'd my chat window go? Bring it back. But it was about 65% or so, 15 people were saying parts count method, and then a little bit less on standards based and no failure, and only one admitted to doing guessing. Bring the presentation back up. But yeah, there's lots of ways to do it, and I'm calling this batch basically, not so good methods, and I hope it becomes clear why I don't care for these methods. And then I'm going to talk a little bit about some of the methods that I think are a little bit more better, to use my my West Coast English here. So guessing, there's nothing wrong with guessing. It's a technique. We take a look at a new product, a new construction, when we're doing failure modes and effects analysis, when we're heading into the HALT lab, when we're just experimenting on the benchtop. We're doing a lot of experimentation, and it's probably not documented thoroughly. It's not formal or anything else, but as an engineer pushes a button and says, will this work? It really is just a guess. And then if you say, well, will this work if I push it a bunch of times? Well, I'm making a guess, and then I'm running an experiment to confirm that guess. So guessing's like a hypothesis. You could use a fancier word for it, but what's the chance that this design will work? The engineering team and the design review group, if we had no other prediction method whatsoever, they're going to sit around the table and go, well, do you think it's going to work? And everybody's going to nod their head, yes or no, and thumbs up or thumbs down, and they'll ship the product or not. And you'll find out if it doesn't work in the marketplace, yet that's a viable technique, and it's something that people actually do. And so it's when it's based on good experience, it's not too far off. Now, we may miss things. It depends on who's making the educated guess, but and it doesn't come with a paper trail, and if you're working with a vendor and you say, well, will your component last for 15 years in my application? And they go, yeah, we think so. And that's all the evidence that they give you. Well, it's not real comforting, right? It's not real satisfactory. Yet we hear that all the time. Vendors and customers are having these discussions, and somebody will say, well, we've shipped 14 billion of these components in the past, and they seem to be working. We haven't heard anything back from anybody, so we suspect it works. Well, we don't know whether it's going into landfill or is it working on very short applications? Will it work in my application? All those kinds of things. But we certainly see a lot of guessing. Now, parts count prediction. Now, this is um, there's all kinds of variations of this. There's the Mill Handbook 217 out of the I think originally out of the Air Force at one point, but it's morphed into being more generic, and I believe it's still a active standard. And I know there's a team working on a revision to it to move it more into the physics of failure type world. But the idea is that you collect the failure rates for the various components that you have in your system, and you add up the failure rates, and voila, you have the system failure rate. And the theory is great. And if you've got really good component level failure rates for your products in your application with your customers, which some companies do because they do all of the repairs of their own components and products, uh, this actually can be pretty decent as a prediction. Now, Mill Handbook 217 and Telcordia and all of the variants of these parts count predictions generally in the document itself says the result is not a prediction of future performance. It's sort of like the stock market ticker that I always tell you is like past performance is no indication of the future, is no guarantee of future performance. Well, parts count prediction is usually looking at a database or a history of similar parts and similar applications. So the closer that is to your situation, the better. But even then, it doesn't take into account the nature of designs. So if I have 100 components in my system and one of the components is only used during testing in the factory, but if it has a relatively high failure rate, it will, on a parts count prediction methodology, it will ding the overall system reliability and make it look bad. Now, when I first ran into parts count predictions and I was asked to do this, I was skeptical at best. And so I went through the mechanics and learned how to do it. And then I went and asked my mentor, what's with this? How can this possibly work? And he said, it doesn't. It, it is wildly inaccurate. And then later, Jeff Jones and colleagues, and he's a professor, and I've drawn a complete blank of where he teaches in England, but he's also active with the IEC Dependability Standards Group. Um, went through a bunch of the different parts count methods and followed the process for boards that they had really good field data for. So they already had how it actually performed in the field, and then they did parts count predictions. And they were finding that the results compared to actual were off by as much as 600%. I think it was minus 100% to plus 600% or some huge range of inaccuracy. And what my mentor told me about was that, yeah, they're not accurate. He says, but they drive the right behavior. If you do a prediction early in the program for an electrical engineer, it helps them to keep the temperature low because that generally helps the failure rates keep low. And it requests that they use fewer parts. So to make a circuit more reliable is keep it simple. Use as few parts as necessary to actually perform it and keep them cool. And those are both good things, but it doesn't really give you a final answer as to what the system failure rate is. Now, there's all kinds of reasons that parts count predictions based on the assumption of a constant failure rate is bad and just inaccurate and all that stuff. And there's work in some areas to make improvements on that, and that's all good. But keep in mind that the basic parts count prediction methodology um, makes a bunch of assumptions that, unless they're perfectly true for your circumstance, it's going to taint the results that you're getting. Now, you may still do it. It may be part of what you need to do to influence your design team to keep things cool and to use less parts and to focus on areas of high risk. Yet, uh, at the end of the day, we've got plenty of evidence over and over again for the last 30, 40 years that says this methodology just is so inaccurate that don't use it to advertise your product's durability. It's tantamount to just lying. It's so bad. So if you're doing parts count predictions, I hope you're in the camp that it's for good to help influence your design and make it more reliable, but not for your data sheet. So I won't ask for raise of hands on which one you're in there, but take a close look at what you're getting out of your parts count prediction and why you're using it. All right. Standards based. There are zillions of standards out there. IEC has got a bunch of standards. The French have standards. The British have standards. The British Standards Institute, BSI, I think it is. There's IEC, IEEE, ANSI, ISO. The Chinese have a whole raft of standards. The Japanese have standards. There's standards all over the place. Now, the ones I'm most familiar with is out of, say, the telecommunications industry. And they said, if you're going to put a device in one of our systems, you have to pass this suite of tests. So it's got to work in hot, humid environments. It's got to work in cold and dry. It's got to work under these electrostatic discharge environments. It's got to work, and on and on and on. Military's got one of those that's out there, and it lists, I don't know, it's like 30 or 40 different tests, from moisture exposure to salt fog to shock and vibration to ballistic impact, all kinds of cool stuff. Um, take a close look at those tests. And I was just doing this with a client last week, as they said, we've got this new component, this interposer to connect two boards. It's a new technology, and we've asked for reliability data from the company. So they sent me a report, and it had 15 different tests in it. They were all IEC-based tests, and there's standards, and I wasn't willing to pay the couple $1,000s to go buy all of those standards, but they listed in the test report how they did it. And the basic steps of temperature, it was, I think, 60 degrees C for 500 hours, and then they kicked it up to 70 degrees C for 30 hours and something like that. And they put the components in trays in the oven, so they weren't connected. They weren't under any stress. There weren't any electrical impulses going through them. And they pulled it out, assembled it into test boards, and measured contact resistance. And the two units that they tested that way both passed. And so their conclusion was it's reliable. And so if you were like me, you'd say, well, how reliable? For how long? And how does it work in my application? So I called them and said, I went through your test report. It's very impressive. You got all these different things you did to this thing. But one test you tested 5 samples, one test you tested 2 samples, and 13 tests you had 1 sample. And he says, well, it's expensive, and it takes time to do these things, and so we limited the number of samples. And so I showed him a quick set of calculations, and I said, if this test, one of the tests that they were running, represents a lifetime of my product, which I have no way of knowing if it does or not, because there's not enough detail here or a model, you're saying that you're 60% confident that we will achieve for one connector at least 38% reliability out over the 5 years that we expect to use this product. Is that your reliability claim? And here's the math. And there was a long silence on the other end of the line and says, well, we know it's better. Um, we've shipped lots of other products and nobody's complained. Trust us. And I didn't have any doubt not to trust them. It's just that their evidence that they offered was pretty darn poor. Now, they thought that because we met the standards, in some of the tests, the standards actually do call for very small sample sizes, and we didn't see any failures. We didn't do all that stuff. So then I said, well, you've done a lot of work and you've done a lot of engineering. How do you expect this product to fail? What's likely to fail? What's your FMEA? What's the risk analysis? What's the first thing that will fail? And again, a long silence. And I think they put me on mute. And the marketing guy was probably coaching the engineers in the room. And then came back and says, well, we don't expect it to fail. I says, well, that's all well and good, but everything fails. So is it going to be the plastic housing? Is it the metal relaxation? Is it corrosion? What's the failure mechanism? And he came back and said, well, we ran 15 different tests that tested all kinds of different stresses. I said, well, that's great. But if your failure mechanism is not excited by any of those stresses, how do I know these tests are even relevant? What if it's something else that causes them to fail? And conversation went on for some time, and they went back with some commitments to figure out how it fails and come back to us. But just because you run an impressive suite of standards-based testing and nothing fails, what have you really learned? What do you really know? How do you translate that to use conditions? So I look at standards as a starting point to the typical things done for that particular industry. Now, the standards were probably written by, a handful of small committee, and you know how committees are, 10, 15, 20 years ago originally, for technology that probably doesn't exist today anymore. So why 85C and 85RH for 1,000 hours? What does that really translate to for my product today? We don't know. The standards don't typically tell us that. So if you're using standards-based testing, it may be a requirement, customers may be expecting it, all those kinds of things. But it's there, it's part of it. So you said it's a business decision. I didn't see when that popped up. What are you referring to there as a business decision versus a technical developing decision? Gives me a chance to get my coffee here. And it's a business case. So yeah, doing a suite of tests is important, right? And we get a bunch of passes, but what are we really deciding on it? I mean, if we bring, like these guys that I was working with, they had 15 tests. But when you looked under the hood a little closer at it, they didn't know what they were testing for, what stresses to really apply, other than a suite of tests they thought would be good. But it's still a business decision. Is it good enough or not? So by providing really poor information into that decision, what's the chance that they will make a good decision, right? You also see it where it's done fairly well. The first product gets really evaluated really well. You do good accelerated life testing. You come up with a conclusion that we know it'll last 5 years with 98% chance. And over the years, that test is always used. And then the argument becomes, well, if it passes that test, it must be good because it passed our previous products passed that test and they worked. Well, I'm using different polymers, different assembly techniques, different applications. I think we'd lose sight of that. We got to focus on not just passing the test. And I agree that marketing and business, they love passing. They don't want to talk about failures. Yeah, and marketing, yeah, I agree. It's cost and timing. They want to get to the market. The business guys want to get to revenue. Um, Yet, I mean, you all look at the news as often as I do and hear about product failures and recalls and so on. Why were they shipping products that were going to fail so spectacular? Now, in some cases, it's we just didn't know and we couldn't know, and they did due diligence. Yet sometimes it's they rely on really poor data. Uh, and I point to standards-based testing as a source of that. Is I've seen it so many times that, well, we don't understand why it failed. We tested a unit during development and or 20 units during development and they all passed. Well, that's all well and good, but what about your manufacturing variability? What about you shifted manufacturing site, you changed the design, you put in a new material. So this all it irks me that just because I used a standard, it doesn't necessarily mean anything concerning reliability. Right? Yeah, sure, put it on your data sheet, but don't claim that it's reliable based on standards. And then no failure testing. And this is an offshoot of standards-based testing, but some teams will say, well, I'm going to test 22 units. And they do some work and figure out, say, like it's a hinge or a mechanical device, and we expect this device, like a button, it will be pushed 1,000,000 times, use a nice big round number. Now, they may or may not know that it will actually be activated that many times, but let's say they do, and they expect it to be 789,000. So they round it up to a million to give it some buffer. And so they go push the button 1,000,000 times. Now that replicates one lifetime. Now, if they do the statistics and they do based on binomial with 0 failures, if they test 22 units, they can conclude with 90% reliability or 90% confidence that that sample represents the population, that they have at least the lower bound to their reliability performance will be 90%. Now, I can use that same formula, and there's a couple other magic numbers. I think 77 is 95, 95, and there's a couple other pieces in there. The trouble is that if you don't have failures, um, did the test evaluate the failure mechanisms that are most likely to cause failures to limit the life of the product? So if I don't apply the appropriate stress, uh, I will pass the test, yet it will not provide information about how long something will last in application. So using the button example, the engineering team says, there's no way I'm going to sit in the lab and push this button 1,000,000 times myself. So they set up a little pneumatic hammer and cycled it on and off really fast, and they pushed the button 1,000,000 times. It took them about 3-4 weeks to do it. And then the product went to market, and the buttons failed in about 2 or 3 months with maybe 5 or 6 thousand actuations. And it was because of the angle of attack and the amount of force that real people exerted on that button. And they broke these things off, and they broke the the connector piece. The actual actuation piece actually fractured fairly quickly. So if you're designing a task, whether it's for no failure or success type testing or any kind of test, does it create the same failure mechanisms that you are expecting to see in the field or that you actually see in the field if you have that luxury? So setting up and running a success test, as I call them, or no failure testing, um, is often we have to because we just don't get very many samples, and it is a very expedient way to get to results. But it comes with the caveat that you really, really, really know the failure mechanism, and you know that the stress that you're applying will eventually create that failure. And so if I have a good solid model and understanding, there's nothing wrong with this kind of testing. It's just that as the product changes and as the product environment changes and as the usage profile changes, the test has to change. And we often lose sight of that. So what I see is a deviation is that we get a good test that actually is meaningful for us. We streamline it to a success type test with no failures and minimize sample size and get the most information from it. And then we make it a standard, whether it's an international standard or an internal standard. And eventually the product changes underneath it and the standard doesn't change. And that's where I see the real problem with this basic approach, right? So does this all make sense? The questions I'm raising here and the things that are coming up, is this starting? I mean, hopefully it's ringing true for all of you. Yet I know that you face hurdles, that these are expected, they're required, you're being told to do them. And so, I mean, what do you think? Thanks, Keenan. Yeah, and cost and time, history, legacy, those are all barriers that come in, you know? And as I'm going through there, as I hinted at, what was missing from a lot of that style of testing is the failure mechanism, right? If we're going to predict the future, um, and I've got a laptop computer, well, and I've got a warranty that's only, say, a year, and I need to come up with a number that the finance team can use to do the appropriate warranty accruals and set up the appropriate handling of failures for, say, a laptop with a 1 year warranty. This prediction is very, very real. It's a lot of money in some cases. Yeah, Neil, we've always done it that way. Is I almost always want to just stand up and yell at them, but I found that that doesn't really work very well. But how about looking at your history and is this still providing value? Is this test actually helping you make better decisions? So if we're doing a success test or a standards-based test or whatever, maybe negotiate for, let's run it to failure, right? Let's just force it to fail. Maybe not quite as severe as a halt test, but let's run our testing to failure and see what fails. And if we don't get anything for a very, very, very long time, why are we doing this test? And let's step back and look at FMEAs and all of the risk assessments and engineering knowledge we have about what should fail and start connecting those dots of, would this failure mechanism occur in any of our testing if we let it run long enough? And then there's that third piece is, well, how does our stress in the actual use translate to what we can do in the lab? Are we going at it with the right angle, the right forces, is the right combination of stresses? All of those elements are good questions to ask. Yet, if you can't tell the story of, we're doing this test because it accelerates or it evaluates the presence of this, and this failure mechanisms, and if they show up here, it means that here's the model that translates it to it's good for 2 years or 5 years or whatever. Well, I don't have a convincing story then of why I'm doing that test. We've always done it this way. It worked on the last product. Customers demand it. Yes, those are all roadblocks that we get and hurdles that we face. Yet at the end of the day, when you sit down with a decision maker, is they're looking to this test data, basically, these predictions and or the testing that support our predictions to say, will this product work long enough with the low enough failure rate? And we should have a pretty decent story to tell there about what's likely to fail and how we know, and map that out, right? And it should be better than a guess. Well, I think it'll work, right? So if you connect to the failure mechanism, you're probably on the wrong track for making a viable prediction. Not you personally, but your organization, the people that are putting together these decisions, right? So the British Ministry of Defense has a standard, and I think I put it in my last webinar. I had the link to it. might be able to find it again and post it here, is called a reliability case. So what they're doing is saying, hey, vendor, you're making this widget for us. Here's our application in our environment. What's the story? What's the equivalent to a legal argument, logical, scientific based, fact supported, data driven story that says your product will work in our environment according to these specifications? 98% will last 2 years. And if they just say, well, we ran the standard test, it should work. Well, there's a big leap there. Well, it should just work. Well, what's the evidence? What's the connection? What's the logic that says that that test means it works? Or your parts count prediction means it'll work in our application? How do you rationalize the connection? That really, really comes back oftentimes to the failure mechanism, right? So the simplest one that marketing guys don't like and design engineers don't like too much, but once they see failures, then they know what to do with it, is test to failure. Now we could be doing halt or stress testing or discovery testing, find where the failure mechanisms are. But if we're doing a sequence of testing, let's run them out to failure. Now, if you only get one sample and they want it back in working order, you're going to be blocked out from doing that. But if you know that a particular pump or a particular circuit board is a weak link in the product from your risk analysis work, then get those components and run them to failure. Now, in more exotic cases, then your prediction of the future might rely on analytical methods and prediction methods using physics of failure type modeling. And we'll touch on that in a moment. But your best bet for predicting the future is evaluating your product until it fails. And does that failure make sense in the use application? So there's some real engineering, material science, engineering work to figure out, did this evaluation or test create a failure that's relevant? So if I'm increasing temperature in a halt test and I melt something, that the phase transition is 500 degrees C above my use application, well, that doesn't make sense for use application. But if I'm only 5 degrees C's over where we expect products to be used and it melts, I probably have a problem. So test to failure. Find what fails and when it fails, and then evaluate that failure mechanism to get your prediction. The other one is classic, is the accelerated life testing. And there's lots of great references out there. There's lots of ways to go about doing it. But it always, in my mind, always starts with, well, what's the failure mechanism? So if I want to evaluate an electronic circuit, and I know that the IGBT, say, in my inverter is the likely component to fail, and I do some research in the literature and I find that the die attach, which transfers the bulk of the heat out of that component due to thermal cycling, will crack and eventually separate, then I lose my heat transfer and it'll destroy the component. That's a specific failure mechanism due to thermal cycling. So it doesn't really matter how long I run it at constant temperature, constant load, I won't be exciting that thermal cycling metal fatigue failure of the die attach. So once I know the failure mechanism that's most likely to cause the problem, or the top 3 list, then I can design a test to evaluate it. But running a suite of tests, I may limit my ability to evaluate the thermal cycling. Right? I might only get a handful of samples for a limited amount of cycles, which really won't excite the metal fatigue cracking phenomena. So by focusing in on what's going to fail and designing my tests to evaluate them, to create the lifetime to failure distributions, now I'm creating a reasonable fact-based prediction of how it will perform in the future. But accelerated testings, it can be expensive. It really, really can. Yet, if you need to make a decision that this product will meet your warranty period or meet your customers' expectations, like those Italians with their bridges, if they didn't believe that this product was going to last for 20 years encased in concrete in the Italian Alps, they weren't going to buy it. So it was a critical business decision. And we could have said, hey, we ran all these standard tests, it should work. And they came to us and said, basically, that won't cut it. You need to prove that it'll work. And hence we did accelerated life testing and put together the chemistry, understanding the activation energy, and modeling the degradation process with plenty of empirical data to back it up, that then created the model that we used then to evaluate the ongoing production and other products. We had a decent physics of failure model of which then to start the evaluations of other products. So it came in really, really handy over the long term. But don't shy away from proposing and designing accelerated testing, because in my mind, it's the best way to predict the future. It's our way of cheating time. But one quick story here is when ball grid arrays, it's an electronics component package that has, instead of leads around the periphery of the package, they were underneath, little spheres of solder. And the one we were using wasn't very exotic. They had, I think, 256, 254 solder joints underneath it. And it was for a printer that we're designing. And it was the first time that we were using one of these in inkjet printers. So I was asked to run an accelerated life test to look at the solder joint life of these products. And so I went away and I did a bunch of testing. We did all this thermal cycling. There was a bunch of literature out already on life testing for solder joints like this. And we saw a couple of failures and had a nice Weibull plot. It looked wonderful, right? So I'm presenting all this information and data. The conclusion was that there was like a 99.9% chance that they'll last for a year. And it was like 98% chance they'd last 5 years or something like that. It was assuming we assembled them correctly and didn't have shorts that opens in the assembly process. If they're assembled correctly, they're just pretty solid. They're just going to last a long time. And so one of the manufacturing managers took out his keychain and took my sample board and was trying to pry off the component. There's a little lip around the edge of it, of this little daughter card that holds the circuit. And so he would stick the key underneath it and he was breaking off the laminate. The solder joint's held. And he says, well, what does it look like underneath? I'm trying to get it off. And he could do that with other components. If he had a gull wing leaded component, he could stick his keys under it and then pop it right off. It was a different structure. And this one was very, very strong, just straight lifting, this axial lifting he was trying to do. And so I noticed him doing that, and I took the board and I twisted it. I just grabbed both ends of the circuit board and rotated my right hand clockwise and my left hand counterclockwise and just twisted the board twice and then lifted the component off. It was a completely different failure mechanism or set of stresses that would cause it to fail very, very quickly. And car keys no longer worked to pulling parts off of a board. And it goes back to is make sure that your evaluation and prediction is related to the relevant failure mechanism. So if you're trying to break something, make sure that what the stresses are will actually cause that break or that fracture or that fatigue or that corrosion or whatever. It's way too easy to run a test that is missing, say, one of the critical elements. So if I'm trying to do corrosion, but I put it in a dry atmosphere and I need moisture to cause the failures to occur, by eliminating the moisture, I eliminate the corrosion path. And I can run the test and I say, hey, we ran 1,000 units and none of them showed any signs of corrosion. Well, we ran a test that actually preserved them rather than corroded them. So it's that kind of, when you look at it that closely, it should be blindingly obvious. But way too many times it's you got to think through it. You have to sort out, does this test matter? Now, once you do a good accelerated test and you understand the chemistry or the physics of what's actually happening to your product, create a model, write down the formula, derive the first principles if you can. And that's called physics of failure modeling. It's been around since the 60s. The folks at University of Maryland CALS have been long-time proponents of this. There's been listening to an Australian podcast lately, and he keeps saying there's a whole heap. So there's a whole heap of literature about failure mechanisms and the models that describe them. It's a great way to get a good picture of your prediction. It's if I know that I have solder fatigue and I know that I'm doing a 20 degrees C daily temperature cycle, there's a decent model out there for solder joints to predict how long they'll last given that thermal cycling. And you may need some more technical information about how big your component is, the types of connectors and the geometry of your solder joints and so on. Yet you can probably calculate it and get a really good sense of where you're at. Now, if you've created the models yourself on your products and on your applications, now you can translate for a customer comes in and says, hey, we want to run this product at 30 degrees C daily temperature swing. And we can recalculate it and says, well, here's when we expect the first percentile of products to fail will be at this point in time. So you're 99% reliable up to this point. And you don't have to go back and run any tests. You've got the model and you can predict it. Now, like any model, back to the standards-based type stuff, is they probably have a limited application. So as we continue to evolve new components, new materials, new all these different things, the models have to keep up to date. Yet it's by using the limited number of samples we have and using the literature and the work that so many people in this group and other places have already done, cataloging it into the physics of failure models allows us to save an amazing amount of time for our products, with the caveat that we keep it current, keep it accurate. So in order to get meaningful reliability predictions is focus on the failure mechanism. And if you've got a model, that's great. If you don't, get one. And it's accelerated testing primarily. But run it to failure, understand if it's relevant, understand the chemistry and physics, get the material scientists involved. What is it actually occurs so that you can explain in a very clear way that your product will fail because of this oxidation process on these molecular chains at these temperatures at this rate. And here's the evidence that supports that. We ran it at 3 different temperatures in these ovens, and it translates back to use conditions in this way. And then you can go to Italy and see bridges that are dry. At least that was my experience. But you got to know the failure mechanism. So I'll leave this screen up. Let me pull up the links and stuff that are in here. And next month, I actually remembered this time. It's been over a year I've been doing these webinars, and I always say, I wonder what next month's webinar is going to be on. So I looked it up prior and added the slide. So I hope you join me for next month's webinar on alternatives to MTBF. And those of you that know me from the knowmtbf.com site know I've got a bit of an opinion on this. So we'll explore what else can we use instead, because that's probably the most common question I get is, well, if not MTBF, what do we do? We'll explore that. So what do you think? You're going to take another look at your testing and your prediction techniques? You know, is it off to the Ouija board or to the crystal ball? Maybe that makes more sense. hopefully you can make an argument that you need to break things, which I find really, really fun. But if you can create meaningful information out of that, well, go for it. If the if the decision is a $1 million decision, it's worth investing to get good stuff there. So I see a bunch of people typing, but I'm not seeing anything yet. Agreed, good. So over on the right, on the lower right-hand corner, you have links to the podcast network I mentioned earlier, the new Accendo reliability site. Oh, I should mention, if any of you are members of the Accendo reliability site already, I'm in the process of moving the membership login information to the new site, and I'll send out directions once I get that set up. And I know that a few people have already found the new Accendo reliability site and have joined it. Excuse me, thank you. But if you're already a member of the previous site, which was off of my business site, I'm moving it, and the podcast is by far the most exciting thing I think over there. So there's interviews and discussions that I hope you find valuable. So everybody, thank you, appreciate it. Yeah, Andre, I've got a couple minutes. Yeah, functional safety. Andre, I might, yeah, let me see if I can find you. If you've got a microphone, let me give that a try. Let's see, I think my list is alphabetical. So, Andre, if you got a second and you're willing, I'm going to unmute you. I think you're listed as Andre too here. So, Andre,
Yes, you can hear me?
yeah. So, what do you mean the functional safety is forcing our
Well,
predictions?
the thing is, we had a proliferation of functional safety standards in Europe, and basically I kind of keep joking that threw us back 20 years in
Hmm.
reliability profession, because you basically have to calculate that cell or a cell, depending on which type of standard you're dealing with, and you have no choice other than doing reliability prediction well before the hardware is built. So
Hmm.
it, like
Hmm.
I said, it kind of gave it a second life, even though I mean, probably most people on this call understand that the reliability prediction using handbooks is not really, uh, it's a very valuable activity.
Hmm. Well, I've run into that with it was a system that actually monitored a like chemical plant or a factory and looked for like a pressure vessel going critical. And they had that SIL certification algorithm, and they weren't they weren't using handbook type stuff, even if it was a relatively new design. Is they had to support it with their own use of those components or testing data to
Yeah,
say
we do
here's what
too.
this failure
Absolutely.
mechanisms. Yeah.
Absolutely, we do too. In fact, I developed a tool for that, specifically for that purpose. But the problem is, a lot of customers actually want you to do specific, like most of the German customers, they want you to do SN 29500, which was developed
Hmm.
by Siemens, which in my opinion is probably the absolutely worst reliability handbook out there. But since it was developed in Germany, then basically you have to use it. So
Right,
I
right.
have to run, but I just wanted to make a comment. Like I said, I pretty much agree with 100% what you're saying. But the situations like that when there's really not a whole lot of options we have in doing those activities.
Yeah, yeah. I don't have a good. And I see Kirk's message here too is that, if a customer is asking for meaningless data, what do you do? And one end, it's a condition of sale. You have to do that process. Um, I think it's a do that and here's the real information. And I think over time, we'll move away from asking for the wrong stuff.
Well, like I
Sometimes, though,
said,
it's
it's that was the hope, but it kind of working the opposite way. Like I said,
yeah,
with those standards developed in Europe, it just kind of threw us back in time.
Yeah,
unfortunately.
that's true. Well,
Okay.
unfortunately,
Hey, Fred,
Volkswagen's not
thank you.
helping.
It was very good
All right.
presentation, and I have to run. Thank you.
All right. Thanks, Andre. Talk to you
Hmm.
later.
Bye.
Bye bye. Yeah, Kirk, I agree. It's educating the customer. It I think what I've seen what Andre's talking about though is where the customer is a purchasing agent that's not technical at all, and they just want to fill out the checklist basically, you know. So it could get ugly real quick of do this or you can't buy the product or we won't buy the product. Well, then you do that. That's in some industries that's the condition of the sale. uh, doesn't mean that we need to ship products that won't meet their reliability expectations, which may take a different level of work and predictions. So I think it's an and type thing. Yeah, and if you the cost of getting the data. So Bennett, that, I've on the Ascendo reliability site, you'll see an ebook that talks about value, finding value. I think is the title. And it's free if you do a shameless plug for the site. If you sign up for the free membership, you get access to those ebooks for free. But the idea is that, well, if the customer is not willing to pay us an extra $50,000 to help them understand the chance of failure of the product in their application, it probably only takes a handful of failures in their factory or in their application before they spend way more than $50,000. Now, the cost of failure to a customer is oftentimes orders of magnitude more than the cost of the product. I mean, they're buying that product for a service or for a feature or the value that it provides them, which has to be more than the cost of the product. I would say that tentatively because I'm sure there's counterexamples. But the notion is that they're making an investment so they get something in return. And when a failure occurs, they lose more than what they can recover under warranty. So it's in their own best interest to get a good picture of the reliability of a product. Yeah, and so it's a challenge, and it's something that we're all facing. So yeah, Sean, I see your note here. Yeah, technical people ask for the wrong data, hence people asking for MTBF, which makes me cringe. Um, yeah, you know, yeah, Sean, hope you join me next month exploring the alternatives. I think we'll have fun there. But you're exactly right. Um, I just wrote a blog post that seems to be getting a lot of nice traction on the nomtbf.com site, uh, talking about the MTBF conspiracy theory. And it's kind of a tongue-in-cheek poking fun at why so many people are using MTBF. Is this you know cobble of power brokers that are forcing us to use it, unbeknownst to us, kind of thing. I don't think it's true, but why is it so prevalent? And what we know it's not terribly useful or nor accurate, yet it's nearly every day I hear somebody say, "Oh, what's the MTBF of that hard drive?" And I cringe because it's such a silly question. And even if somebody says it's 858,000 hours MTBF, it's pretty meaningless to how long it'll last because the nature of the failure mechanisms don't relate to MTBF, to the way we commonly interpret it. Yeah. Yeah. Sorry to hear that, John. Hope you get better. I wish there was a little. I should maybe make some breath mints and call them the anti-MTBF pills or something like that. Yeah. But yeah, you can run exponential on it. It's back to that failure mechanism. Is it relevant? Does it make sense? You know. So anyway, um, I'll stay online. I'm going to thank everybody for attending. We'll hope to see you next month. I'll leave this screen up, and I'll stay online. I'll be monitoring here.